Hello everyone, thank you for watching this video. My name is Brent Griffin. This work is done in collaboration with Jason Corso, and today I'm going to be talking about how we use off-the-shelf detection methods with camera motion to solve for depth. Let's look at a concrete example. Assume we want this HSR robot to grab the cleaning solution off of the shelf. Here's what the world looks like to HSR. Using faster RCNN, we can determine where the bottle is located in image space, but HSR needs a 3D location of the object to plan a trajectory for grasping. On the other hand, if the camera is moving, we can solve for depth by comparing changes in camera position to changes in detection, which enables HSR to determine the 3D position of all detected objects. Furthermore, using our object depth via motion and detection dataset, we train a single network to perform detection-based depth estimation across a variety of application domains, including robotics, driving, and even experiments with a camera phone. Next, let's talk about how it's even possible to find depth from motion and detection. Using our motion and detection model, we'll show a few different examples. Assume that we have an object in view of a camera. Using object detection, we can find the bounding box for the object and determine its scale using box height h1 for the camera's current position p1. Notably, if the camera moves closer or further away from the object, the bounding box scale will change with the new camera pose. If we can measure the relative change in camera pose, for example from vehicle odometry or robot kinematics, we can compare camera motion to changes in scale to solve for depth using the following solution. To understand this intuitively, think about walking towards an object that is far away versus up close. A closer object will expand rapidly, but a farther object will remain relatively consistent for the same amount of motion. The rate of change in scale per observer motion is what determines the depth. Thus, this solution capitalizes on a very specific depth estimation cue, which psychologists call optical expansion. We can also determine depth using motion parallax. Let y1 represent the vertical offset position of the object's bounding box for the initial camera pose p1. If the camera moves laterally, this offset position will change. Using this motion parallax-based cue, we can compare camera motion to changes in bounding box offset position to solve for depth using the following solution. While these two closed-form solutions help illustrate the underlying depth estimation cues we use in this work, these approaches do have limitations. For example, what if the object is moving, or there are detection errors, or there are more complicated camera motions? To address these limitations, we introduce the object depth via motion and detection dataset, which enables learning-based techniques to be applied in this new problem space. ODMD data consists of a sequence of n observations, with each observation including a 4-parameter bounding box and an XYZ distance for the relative camera movement between each observation. Using this input formulation, we can use an absolute depth loss to train our network to predict the ground truth object depth for the most recent camera position. However, we find that using a dimensionless loss, that is, predicting the depth relative to the overall input camera movement, leads to the best performance across applications with different movement scales. Finally, if we normalize the input bounding boxes by image width and height, we find that our trained network generalizes across applications with different camera parameters. This overall formulation has many benefits. First, the network input consists of only bounding boxes and movement distances, so we can easily configure and generate simulated training examples with ground truth labels for just about any target application. We also simulate detection errors by adding perturbations to the training data. These perturbations teach the network to determine which input observations are reliable and leads to the best overall performance in real-world applications. Finally, because the network does not require actual image data, we find that sim-to-real transfer is achievable with low-complexity architectures. In our paper, we show how we achieve state-of-the-art results after less than 4 minutes of training, and at inference, process thousands of examples in just a few milliseconds. For evaluation, we introduce an ODMD benchmark with over 20,000 examples across 4 validation and test sets, including mobile robot experiments using an end effector camera to locate household objects. As an added challenge, we test our method on an existing benchmark dataset by converting segmentation masks to bounding boxes. Notably, our D-Box network achieves the best robot, driving, and overall result on the ODMS benchmark. Furthermore, while the second best method takes 2.6 days to train on segmentation masks, D-Box trains in under 4 minutes by using a simpler, bounding box-based input. Thank you for watching our video. If you'd like to use ODMD in your own work, please visit our GitHub page at the address shown here. And if you'd like to learn more, we recommend checking out our paper. Thanks.